We're going to look at question 6 of the 2023 A-Level Further Statistics paper. It's a question about probability generating function. It might be a concept that many of you are not familiar with, but as long as you understand the basic premise, there's also quite a lot of hints in the formula booklet, and we'll take a look to see whether that will help us. Although it's quite a long question with 13 marks available, let's not be intimidated by it. We're just going to do it step by step. And if you're careful with your arithmetic, if you follow the hints in the question and also in the formula book, you should be able to get most, if not all, the mark. Let's look at part A first. In part A, we're given a discrete random variable x with a certain probability generating function, and we are asked to specify the distribution of x. So before we proceed any further, whenever we are asked to specify a distribution, it's not enough just to say whether it is, for example, a binomial distribution or a Poisson distribution. We always need to specify the parameters of the distribution. Why don't we take a look at the formula booklet? I'm in the section where it says statistics. In the table that is given me some standard discrete distributions, binomial, Poisson, geometric, and negative binomial distribution. And more importantly, PGF, the probability generating functions of all of these standard discrete distributions. So let's take a look to compare whether the expression in the question, t squared over the square of 3 minus 2t, to see whether we can rearrange that so that it's close to, or if not, in the same format as one of the probability generating functions. Looking at this table, I think this expression is closest to what the question is giving us. But in the constant in the denominator, it is 1 here. And also we've got a p in front of the t in the numerator and 1 minus p in front of a t in the denominator. So let's try and rearrange the expression in the question to see whether we could get it to this format. Now we've got the target. So this is our target PGF format. Let's write down the probability generating function in our question. When we see an expression like this, and if we want to get it to an expression like the one in the formula book, the first step that I would normally do is to try and convert this constant, this 3, into a 1, and see what I need to be dividing by in top and bottom in order to make that 3 into a 1. So let's do that together. In order to make that 3 a 1, I need to do that within the brackets in the bottom. So that's 2 over 3t. Now I have factorized 3 out of the expression. So I need to be writing it like this. The top part is still unchanged. Now I'm going to divide the top and bottom by 3 squared. So that becomes 1 over 3t squared. That becomes 1 minus 2/3 of t squared. This is looking promising. Here I'm getting a hint that maybe r could be 2, maybe p could be 1/3. Let's see whether that works. So carrying on with my rearranging, g of t equals 1/3 t. I'm going to take the index of 2 outside of the top and bottom brackets. 2 over 3 is simply 1 minus 1 over 3. And look, this looks promising. Here it confirms that r is 2 and it confirms that p is 1 over 3. Therefore, our answer to the question is the distribution of x is a negative binomial distribution with r of 2, p of 1 over 3. It's actually quite straightforward if you make use of the formulas given in the formula book, and also if you're careful with your rearranging of the terms. Now on to part B. It tells us that a fair die is rolled repeatedly, and it asks us to describe an outcome that could be modeled by the random variable x. So there are a few things that we know about the random variable x. We know that it follows a negative binomial distribution, and we know that the number of successes r is 2, and we know that the probability of success is 1 over 3. We need to know that the definition of a negative binomial distribution with a certain parameter is the number of trials, the number of attempts in order for us to get a certain number of success. And the success is being defined by the parameter of the distribution. And in this case, is 2. So basically, RS2 is the number of success. And X is the number of trials, number of attempts needed. What about the probability P? Here we're saying the probability of success is 1/3. Now, when it comes to a fair die, so there are 6 sides to a die, how do I define success in order that the probability of success will be 1/3? So I've got an outcome of 1, 2, 3, 4, 5, 6. If I want a probability of success of 1/3, we simply want 2 of these numbers to be my so-called target numbers. So if 2 of these numbers come up, my specified 2 numbers to come up, and then I get my success. There are different ways to do it. You could say, okay, what if 1 and 2 come up? What if 5 and 6 come up? What if 2 and 6 come up? All of these could be an answer. But I'm going to do it in a more mathematical way. I'm just going to define an outcome where X is the number of attempts needed to get 2 multiples of 3. So in the numbers 1, 2, 3, 4, 5, 6, there are 2 multiples of 3. One of them is 3, the other one is 6. So there are 2 outcomes that would give me my success event. Therefore, I'm going to define X as the number of attempts in order to get 2 multiples of 3. So I don't know how many attempts I will need. As long as I get 2 of those, and I know that the probability of getting a 3 or a 6 will be 1/3. This is how I'm going to define the outcome that can be modeled by the random variable X. You might come up with something different. In fact, the model answer is actually describing X to be the number of rows to achieve a 5 or a 6. Now we look at part C. Part C has 7 marks, it's quite a lot of marks, but actually there's very little statistics there. There's more calculus than statistics. And if you're careful with your differentiation and with your arithmetic, you are going to get all 7 marks. The formulas to find the expectation of X and the variance of X is actually conveniently given in the formula booklet. So don't try and memorize those because you might get those incorrect, especially during exam conditions. Make sure you check in the formula booklet to ensure you get the right expressions. To our formula book, we're given this. So we've got the expectation of X and the variance of X in terms of the probability generating function and its derivatives evaluated at 1. Let's use these formulas given in the formula booklet. So I've put up here what we've been given in the formula book. Now it looks like we need to work out the first derivative and also the second derivative of the probability generating function. So a bit of calculus here needed. I'm going to say part C1. So we know the expression for expectation of X. But let's just start with the probability generating function of X. I'm going to write this in this format so it's easier for me to do the differentiation. So that's probability generating function. Let's differentiate with respect to t. Make sure that t is a dummy variable. We're just going to be differentiating that, and we need to make use of the product rule. So we keep the first term same, differentiate the second term. Make sure we differentiate within the brackets as well. So that's -2 brackets. And then we differentiate the first term, keeping the second term the same. So that's simply 2t, keeping the second term the same, 3 minus 2t to the power -2. Simplifying the expression, so we have 4t squared times 3 minus 2t to the power -3 plus 2t times 3 minus 2t to the -2. Okay, so that's our expression for the first derivative. Because in order to work out the expectation and the variance, we need to evaluate this derivative at t equals 1. T equals 1 is very simple. 3 minus 2t, all of that is going to be 1, so I don't need to worry about that expression in the brackets. It's going to be simply 4 plus 2 equals 6, because t is 1. Now let's work out the second derivative. Now I need to be differentiating this expression that I've highlighted in purple there. Now we just need to be very careful with our differentiation, making use of the product rule a number of times. G double prime of t equals. Now for the first term, we're keeping the first term of the product the same, differentiating the second term in the product. So I bring the -3 forward, 3 minus 2t, that's 1 less, differentiating inside the brackets as well, is that -2 times t. Now I'm going to differentiate the first product within the first term. So that's differentiating 4t squared, that gives me 8t. And then I keep the second term the same, 3 minus 2t to the power -3. Now on to the second term. I'm going to keep the first product in that term constant, differentiating the second product. So I bring -2 forward, 3 minus 2t -3, again differentiating within the brackets with respect to t, that gives me -2. Now I'm going to differentiate the first product of the second term. So I get, differentiating 2t, I get 2. And I'm just going to keep the second term the same. Now let's simplify the expression I get. So that equals 4 times -3 times -2. That gives me 24t squared, 3 minus 2t to the -4. And actually, I can collect some like terms there. And then the next expression is simple 8t times 3 minus 2t to the -3. The next term is also going to be 8t times 3 minus 2t to the -3 plus 2 times 3 minus 2t minus 2. That's great. Looks like I can even simplify that further. So that gives me 24t squared times 3 minus 2t to the power -4 plus 16t times 3 minus 2t to the -3 plus 2 times 3 minus 2t to the power -2. That's great. So that's our expression for the second derivative of the probability generating function. What if I evaluate that at 1? T equals 1. T equals 1, again, all the brackets go away. I'm left with 24 plus 16 plus 2, so that's 42. That's not the end yet. To work out the expectation of x, actually the expectation of x is simply g prime of x evaluated at 1, so that's 6, so we worked it out earlier. The variance of x given in the formula booklet is g double prime at 1 plus g prime at 1 minus g prime at 1 squared. So what's that? G double prime at 1 is 42 plus g prime at 1 is the expectation, which is 6, minus g prime of 1 squared, minus 6 squared. So variance of x is 12. After all, it's actually quite simple, but we just need to be very careful with our differentiation and the use of product rule, and we'll get the full 7 marks. Now let's look at part D. In part D, we've been given the discrete random variable of y with a probability generating function, and we are asked to find the exact value of the probability of y equals 19. It looks quite an impossible question to ask, but if you know something about probability generating function, you might know that, well, the probability of y equals 19 is simply the coefficient of the e to the 19 term in the PGF being that expression. Well, it's all very well knowing about this definition, but to work out the coefficient of the t to the 19 term will take us a while to work through, even if we know some of the pure maths of series expansion, But we're actually going to use a more clever way to work out the coefficient of the t to the 19 term so that we get the full 3 marks. And by the way, whenever you see a question asking for an exact value, we can't just give a rounded answer. It's likely that that value will be in the form of a fraction. So how do we go about tackling this question? If it was a standalone question, it might be difficult for us to know how to start. But this is part D of a question that's asking us about probability generating function, that's asking us about the distribution of x. So why don't we try and make use of the earlier part of this question? Let's take a look at this expression, the probability generating function of y, and compare that to the probability generating function of x. And we can see that they're not too different. Why don't we try and write a probability generating function of y in terms of the probability generating function of x and also the dummy variable t? Probability generating function of y, t10 over 3 minus 2t cubed squared. Comparing this to the probability generating function of x, it looks like instead of t here, we've got t cubed. And instead of t squared here, we've got t to the power 10. So why don't we put t cubed in the probability generating function of x and see what happens? So what if I have probability generating function of t cubed equals, that's going to be t cubed squared. T cubed squared is t to the 6 over 3 minus 2. So t becomes t cubed. And this is my expression. So that looks very close to the probability generating function of y. And the difference is simply t to the power 4. So if we multiply t to the power 4 to g x t cubed, that equals t to the 6 times t to the 4, 3 to the minus 2t cubed squared. That equals t to the 10 all over 3 minus 2t cubed squared, which actually is my probability generating function of y. So how do I go about using this newfound information? Again, if we're stuck, sometimes if we look at the formula booklet, we'll find some clues. This is a formula booklet, and I'm going to use a definition of the probability generating function. It says g of t equals expected value of t to the power x. Now, looking back at what we worked out in our question, we've got the probability generating function of y expressed in the form of t and also the probability generating function of x. What if I change the dummy variable from t to t cubed? So t has become t cubed. That's simply the expectation of t to the power 3x. What if I multiply left and right by t to the power 4? T to the power 4 times this equals expected value of t3x times t to the power 4. Now, t to the power 3x times t to the power 4 is simply t to the power 3x plus 4. On the left-hand side, now I'm going to bring this expression back to our question. On the left-hand side, you might recognize that that is what we worked out to be the probability generating function of y. So we're going to bring this expression back to our question. So this is what we found from the formula booklet. I'm just going to circle that so that we know this is our new information. That's great because we know that the left-hand side equals the probability generating function of y. So by definition, we can actually write the expression y equals 3x plus 4. So this is a very good transformation. I've actually worked out a very useful expression for you to remember, which is when y equals ax plus b, then the probability generating function of y equals t to the b times the probability generating function of x evaluated at t to the a. This you can derive just like how I did, but maybe it's useful for you to memorize this expression. It's not given in the formula booklet, but just be careful where the b is and where the a is because some people get confused. Now, we've got this expression y equals 3x plus 4, which is very useful. So now, instead of working out the probability of y equals 19 or the coefficient of the term t to the 19 in the Taylor expansion of the PGF of y, we can actually work out a simpler probability, which is y equals 19 is 3x plus 4 equals 19 because 3x plus 4 is y, and that means x equals 5. Now, we can work out the coefficient of t to the 5 in the probability generating function of x, but because we've worked out that x actually follows a negative binomial distribution with parameters 2 and 1/3, we can use this information to work out the exact probability of x equals 5. Now, how do we work out this probability? Again, the formula booklet is our friend today. You may remember how to evaluate the probability of a negative binomial distribution, but if you don't, the answer is given in the formula booklet. For the negative binomial distribution, this expression is how we evaluate the probability of x equals small x. From the formula booklet, probability of x equals small x is x minus 1, r minus 1, t to the r 1 minus p, x minus r. And here we know that r is 2, p is 1 over 3, and x here is 5. So the answer we want is 5 minus 1 is 4, r minus 1 is 1, p to the r is 1/3 to the power 2, 1 minus p is 2/3 to the power 5 minus 2. Evaluating this, we get the probability of 4 times 8, so it's 32, and then 3 to the power 5, so that's 243. So that equals the probability of y equals 19. 32 over 243. And remember to keep it in a fraction because the question is asking for the exact value.